Welcome back to our course, Fundamentals of Operating Systems, based on the textbook Operating System Concepts, 10th edition, by Abraham Silberschatz, Greg Gagne, and Peter Galvin, published by Wiley Publishing. We are in Unit 6 of our course right now, the topic of which is process synchronization. We've already discussed several techniques for process synchronization, and in the last lesson we were introduced to the semaphore. We're going to continue on that discussion of the semaphore beginning now. Previously we found that the implementation of mutex locks suffers from busy waiting, which means there can be an unacceptably long delay for processes. The definitions of wait and signal semaphore operations just described present the same problem, which means there can be unacceptably long delays for processes. Perhaps you've been at one of those road blockages and watched as car after car came from the other end while you couldn't move. I'm betting that you thought it was an unacceptable delay. To overcome this problem, we can modify the definition of the wait and signal operations as shown in the next slide. When a process executes the wait operation, it may find the semaphore value is not positive, so it is delayed. However, rather than engaging in busy waiting activity, the process can suspend itself. The suspend operation places a process into a wait queue associated with the semaphore, and the state of the process is switched to the wait state. Then control is transferred to the CPU scheduler, which selects another process to execute. Remember our discussions about the process manager moving processes from ready to wait and back? To implement the semaphores under this definition, we define a semaphore as shown here. On the left, the structure of the semaphore is defined. On the upper right, a block operation is defined using the wait or V operation on a semaphore. And on the bottom right, a wake-up operation is defined using the signal or P operation on the semaphore. A process that is suspended, waiting on a semaphore, should be restarted when some other process executes a signal operation to increment that semaphore. The process is restarted by a wake-up operation which changes the process from the wait state to the ready state. The process is then placed in the ready queue. Now we've already learned that the CPU may or may not immediately be switched from a running process to the newly ready process. When that happens depends on the CPU scheduling algorithm. Well, that concludes our description of the semaphore, making this one of our shortest lessons so far. Now we're going to continue on into other issues pertaining to process synchronization and some of the problems that have to be faced. So stop now, go back and review your 2 videos on semaphores. Make sure you've got that down pat, and when you're ready, come on back and we will continue.